Okay, so next we start heat equation. So we consider the following heat equation. What is heat equation? Heat equation is solution of this is like parabolic equation, because u is a function of x and t, where for this particular example x is just one dimensional real number. However, one can replace del 2 del x2 by Laplacian, and u would be a function of time t and Euclidean space. Okay, so this is called parabolic equation because with respect to t variable there is only first order operator. With respect to this x variable, which is we call often space variable, we have second order operator and the coefficient is non-zero. Okay, so this is the simplest form of heat equation. This is satisfied on all time positive and all x in R, and at time 0 u satisfies one initial condition. We call initial because time is concerned. So when time t is equal to 0, we call that initial time. So at time 0 it satisfies the initial data. We call f as initial data. Okay, so f. So that is the meaning of heat equation. Okay. Okay, what we are going to do is that we are going to show that for this heat equation also we can have stochastic representation. Okay, so using Brownian motion we can write down the solution of the heat equation as a conditional expectation of function. Okay, this function would be there. Okay, and the Brownian motion would also be involved there. So that we are going to do. So that that would help one in many different way. One thing is that would help one to compute. Okay. However, for this equation actually the solution has closed form solution. One can write down in terms of integrations. Okay, it has a closed, like using error function, correct. But there are more complicated equations, say for example where these coefficients are not constant but variables, etc., that one cannot write down the solution in closed form. One can write down as is elementary integration. Then for those cases what people do, they try to solve numerically. Okay, when one solves these equations numerically, then one has to take the whole domain, okay, and discretize the domain, and then find out the solution of the on the whole domain there. Okay, even if someone does not need to find out the value of the solution on the whole domain, but say I just want to find out the value of the function only at a single point, but still the numerical procedure involves the solving on the whole domain. Okay, and then only one can get. On the other hand, if one takes the stochastic representation, as we have seen for Dirichlet problem, there we do not need to consider the whole domain, because the solution is u of x is equal to conditional expectation of f of w tau d given w0 is equal to x. That means you just take the point x where you want to find out the value of the solution, and then you simulate the Brownian motion and wait till that Brownian motion hits the boundary, and there the location you find out, and at that location you see that what is the value of f, the boundary data, and you continue recording that values maybe a large number of times, capital N number of times, and take average of these values. That would give you an approximation of the expectation. So that would be a numerical approximation of the solution at that point. And for finding out this, you do not need to actually compute the approximate the solution at any other points. Okay. So that is one advantage of stochastic representation. So for computation is concerned. Okay. For those who are seeing heat equation for the first time, the following example and visualization should help them gaining understanding of the heat equation. Okay. Here I do not have the scope of actually deriving this equation from the physical phenomena of propagation of heat. However, I have taken this equation and then solve this numerically, and then the animation might help you to understand that it is really indeed the heat profile propagation. So consider this equation del u del t is equal to half del 2 u del x2. So here this time is 0 to infinity, okay, so all positive real time, and then x is minus infinity infinity, the whole line. So you can think that the material is a thin rod, okay, extended to infinity from both sides to both sides, and then initial data, that time 0, it is maximum of 0 comma 1 minus mod x. What does it mean? That at x is equal to 0, it is 1 minus 0, that is 1, and at x is equal to minus 1 and 1, it is 0. So heat is like 0 at the end points of minus 1 and 1 and beyond. However, inside the interval minus 1 to 1, it is like a triangular shape, okay. So that means the highest temperature is at the origin, okay, when x is equal to 0. And then the solution we are going to see in our successive lectures, that we can write down solution of this equation as expectation of u of 0 comma x plus wt, okay, at time 0, whatever the expression is. So this is known function x plus wt. Okay, so let us see that how does the solution look like. So here it is not easy to draw such a function because it is function of two variables, t and x. However, if we fix a particular t, then as a function of x we can draw. So these are the numerical solution of the equation at time 0. So this blue curve is at time 0, and then if you change time t, say time is increasing 0.1 to 0.2 to 0.3, and then it is increasing 0.4 to 0.5, then that function value at 0 is decreasing as it happens because heat dissipates, diffusion happens, and then that heat is transferred to both sides, and here on other sides, beyond the interval minus 1 to 1, the heat temperature amount is increasing. It will increase for some time and then again it will decrease, because again the more heat would dissipate and then to decrease, and then everything would go to 0 eventually, okay. So this is like the visualization of the solution of the heat equation, and then we know that finally how the solution would look like at a finite time. So time is t is equal to 1, say, okay, we know how should it look like. And here we are now going to see that what is the effect of this formula, that expectation of this, okay. So what is the effect of this formula? So this movie is actually made by finding out expectation, finding out the average, okay. So this wt is the Brownian motion. So we have fixed t is equal to 1, so u1x. So this blue line, okay, so this blue line, so this blue line actually shows the solution at time 1, and this line is the given initial data, and then these red points are, say, given this any particular point x, okay, what is the solution value, okay. Imagine that we don't know, we have not computed the solution, we don't know this value, okay, but we want to find out this particular value using this formula. That means we would like to find a w1. W1 is the normal random variable with mean 0 and variance 1. So we would like to find out expectation of this, okay. So then we take more and more such u of 0 comma x plus w1, and larger the number of such realizations, and then we take the average of those, correct. That is actually sample average, and then the sample average converges to the solution. So let us see how does it converge. So number of simulation, so this is the number of such samples we have considered for considering the average, and as the simulation number increases, so more number of samples increases, these points are coming pretty closer to this, okay, fine. So this is showing that, okay, one can get a good approximation of the solution one can get using the simulation. if one wants to find out that okay, exactly on that curve, okay, visually exactly, then possibly one has to run simulation to say 3000. I mean, I have checked that with 3000 it is pretty close. Okay, fine. So now we have a better understanding about heat equation. Now we go back to our slide. So here we observe that the density of Wt, the Brownian motion, is given by probability density function. Wt is in some, so that is how we find out the probability density function. Probability density function is nothing but the random derivative of the law, okay, with respect to the Lebesgue measure, and that is Pt of x y. Why? Because we fix t, we fix x, and the random derivative is a function of y. So, Pt x y, that is given 1 over square root 2 pi t e to the minus x minus y whole square by 2 t. Okay, so this formula we all know, because this is nothing but probability density function of normal random variable with mean 0 and variance t. Okay, and that we have already seen for in the definition of Brownian motion, that this should be the density function. And if we now compute the partial derivative of p with respect to t, we would see that okay, so these are the product of two terms. So from here we are going to go to minus 1 over 2 t p, okay, and then from this part we are going to get x minus y whole square, okay, this part by 2 t square times p. Okay, so we are going to get this. Okay, so we record this expression here. We also have one assumptions which would be obeyed throughout this part of the study, that initial data has some kind of growth condition. Okay, what is this growth condition? That mod of f of x into e to the power minus ax square dx is finite. Okay, so of course, I mean, we are not here aiming to answer to this heat equation problem question for all possible given function f. I mean, what does it say? It basically says that if f is any polynomial, I mean not polynomial, I mean I'm saying that okay, is growing to the infinity in polynomial growth, then also we know that this integration is finite. Okay, so this would be violated, that means it will be infinite if f grows to the infinity. Grows mean in the sense the mod f goes to the infinity, it fluctuates out minus negative or positive, okay, faster than any polynomials, then we might not be able to assure this finiteness. Okay, so this theory, okay, whatever we are going to derive is under the assumption that okay, the initial data, okay, that is not growing more than polynomial growth. Okay, so here we define u of t comma x as expectation of f of Wt given W0 is equal to x. That means you are starting at the point x. This can also be rewritten as expectation of f of x plus Wt given W0 is equal to 0. Okay, what was the way I have written in those animation where f is satisfying that condition. Okay, we would keep that condition, and then this expectation is of this form e to the minus infinity to infinity integration f of y p of t x y dy. Okay, and this integration makes sense because of this condition on f, and p has e to the power of minus x minus y whole square by 2t. So this is finite, so this makes sense. So we can define this function u. Okay, and here we are going to see these properties, that u has derivatives of all orders. Okay, p is of course smooth, p has derivatives of all orders because it is exponential function, very smooth nice function. But what we are going to say that okay, under this assumption on f, what we have mentioned, does not matter what f is, but if f satisfies that condition what is written in 3, then u defined in this manner is also a smooth function. Okay, it has derivatives of all orders, C infinity function. Okay, next is that computation of the partial derivatives. How does the partial derivative look like? So this partial derivative of u can be computed I mean, you can actually take these partial differential operators inside the integration. So, it is equal to minus infinity f of y del n plus m del t n del x m of p t x y dy. Okay. So, this is also allowed. Okay. So, these are the properties. We are going to see the proof of this. Okay. And also that del u del t minus half del 2 u del x 2, okay, u if you define this way, that is equal to minus infinity f of y del t minus half del 2 del x 2 p t x y, because this comes from just above. Okay. And this part is 0. Okay. So, here del 2 p del x 2 is minus. So, I have already obtained del p del t expression. Here del p del x expression is minus 2 times x minus y by 2 t times p. This is coming because of this, e to the power of minus sign is there, correct. Del x, if you do, you get minus 2. Okay, and then this would appear. Okay. So, this 2 cancels actually, and then you consider del 2 del x 2 of p, then this product. So, from this part you are going to get just 1 over t here and p, and from this part again this term. Okay, so x minus y divided by t. So, x minus y whole square by t square p. Okay, so then if you club this together, then x minus y whole square by t square minus 1 over t times p appear here, del 2 p del x 2. On the other hand, del p del t is often as minus 1 over 2 t plus this term. Okay. So, we see that exactly same expression, that just half is multiplied here. Okay. Half is multiplied here. So, 2 times del p del t is equal to del t p del x 2. Okay. So, here I made a mistake, here it should be minus sign, correct, because this is okay. So, here it is minus sign. So, this is equal to 0. Okay. So, here therefore, from here we know that, okay, this part is 0. So, this u satisfies this equation that del u del t is equal to half del t u del x 2. Okay. On the other hand, so for initial condition is concerned, if you put t is equal to 0, so w 0 is equal to, so expectation of f of w 0 given w 0 is equal to x. So, it is starting from there, and you are, so it is no more and it is just deterministic where w 0 is x. So, expectation of f of x is f of x. So, this function trivially satisfies the initial condition. So, we know that, okay, from this slide that u defined this way is indeed the solution of the heat equation. Okay. But of course, we need to give details proof of this fact that u has derivative of all orders and this expression, because this is also used here, correct. We need to prove 1 and 2. So, for fixed t and x, we first observe that del p del t divided by p is of order of y square. So, it even if it increases, it does not increase more than of order of y square, because del p del t we have written that, okay, as some terms times p. So, let us go back there. So, del p del t is equal to p times this thing. So, it does not grow more than the power of y square, correct. It is parabolic at most. Okay. So, and del p del x by p is order of y, correct. I mean, it does not grow more than that, del p less by p. So, these are the growth estimates which we would require for our proof. So, proof of 1 and 2. Okay. So, we first fix one beta positive and one epsilon positive, and also T naught positive, and T1 is more than T1. So, T1 is defined by 1 over 2 times A plus epsilon. Okay. So, whatever epsilon you choose, we take this way. Okay. And we consider strip. This is strip because mod of x is less than beta and t is between T naught to T1. Okay. So, open interval T naught T1. So, this is an open strip. So on the time axis it is between t0 to t1, and then on the space x it is like between minus beta to plus beta. Is basically a open rectangle. I mean, I should not say strip, it's just open rectangle. Okay, what is important is that t0 is positive, so this is a little away from origin. Okay, and also is bounded, that is also very important. Okay, difficulty arises when it is unbounded, correct? So we are making constructing this set where things are bounded. Okay, so now for every t and x in this rectangle, we call this b epsilon beta, because it depends on epsilon and beta. Okay, why epsilon? Because t1 depends on epsilon. Okay, and a is a positive number. A is the number what appears here, is the same number in the assumption, what appears in the assumption. Okay, so now we would use these inequalities. So let us read this inequality: a times y square minus x minus y whole square divided by 2t is less than or equal to a times y square minus y square by 2t1 plus 1 over t1 times mod x times mod y. Okay, so this part is equal to minus epsilon square a square plus 1 over t1 times mod x into mod y. So here this is y square, correct? A minus 1 over 2t1. Okay, so y square times a minus 1 over 2t1. However, t1 is 1 over 2a epsilon. So 1 over 2t1 is a plus epsilon. So a minus 1 over 2t1 is epsilon, correct? So from this we get this. Okay, so now we understand. I mean, initially it was not clear why did I choose t1 in this fashion. The reason is now clear, that we would like to choose t1 in this fashion so that this difference appears to be epsilon y square. Okay, so that now I have a negative sign epsilon. Okay, so it's like it is inverted parabola. Okay, just to get that we have chosen t1 this way. Okay, and now this is an upper bound of this. So this is 1 over t1 mod x into mod y. However, mod x is in less than beta, so I can have this upper bound that, okay, so this is beta by t1 mod y. So this is even less than, so here see I have still mod y here involved and y square involved here. So this is basically inverted parabola, this y square. However, this second term is like growing, but eventually this for large y, this first term would win, correct? It would dominate. Does not, no matter, I mean, how small epsilon is, but for a large y this term would start dominating than this. However, I mean, you have to wait. Okay, so for after a ball of a large radius, but we can actually try to find out one estimate which is where we do not have first order term. So we obtain that, okay, if we consider minus epsilon by 2 y square and here minus beta square by 2 epsilon t1 square. Okay, so then this is an upper bound. Okay, and for this is below this quantity. Okay, so I am not giving the details here, but this is just a simple calculation. As this t1 is dependent on epsilon, one would get it, and you just need some algebra to complete this part. Okay, so now as t is more than t naught and less than t1. Okay, so 1 over t is less than 1 over t naught. So 1 over t is less than 1 over t naught. Okay, this is also the expression for p. We already have obtained del p del t, del p del x, del 2p del x2, and we have seen that, okay, how the formula is coming. Okay, like p times some terms. Okay, and that if you have say nth order, then you get some to the power of n, etc., that would appear, and mth order with this space also you are going to get this. So x minus y whole square, so this power would increase. So from that we know that, okay, this term, the partial derivative n plus mth derivative, the del t, I mean n del xm of this is less than or equals to some constant times this growth variable 1 plus mod y to the 2n plus m. Why 2n appears here? Because we have seen that with del t del p del t already we have obtained x minus y whole square, correct. However, for del p del s we got just linear term, okay, and then second order we got second order term, okay. So, from that we by induction we know that, okay, we would get the 2n plus m, that is the order, and however there is also one exponential term e to the power of minus this term, which decreases exponentially fast. Okay, so this is the growth property what we are going to use, and this is true for all t x in this thing, okay, for any y r. And here this is very important that this constant we can choose to be finite when my point t and x are from b epsilon beta, okay. So, I am writing t naught also to specify that it also depends on t naught, okay. Why is it so? Because this expressions is not only dependent on y, but also depends on x, okay, and also 1 over 2t. If t is very small, then this becomes very large, right. So, that is the reason that I had to take away from 0. So, t is taken between t naught to t 1, okay. And for this expression also we have this t in the denominator. So, if I now consider only the b rectangle open rectangle b, there x is bounded, okay, and t is bounded away from 0. So, this part we can actually the remaining the whatever that the function is, I can write down as a constant times of this, okay. I can bound this by a constant times this. This constant of course depends on many things. It depends on the value beta, epsilon, choice of t naught, and therefore t 1 also, t 1 depends on epsilon a of course, and also n, m, it depends on everything, okay. So, this constant, okay. So, next what we see is that if we now have f of y also multiplied with this, then we have mod of f y on the right hand side also, okay. Then this mod of f of y is here, and here whatever e to the power of that expression was there in the earlier slide, e to the power of minus x minus y whole square by 2t of this thing, okay. So, a y square minus x minus y whole square by 2t. So, this thing is dominated by minus epsilon by 2 y square minus beta square by 2 epsilon t 1 square. So, I did not have a y square there, I just had this expression, but of course, I can add and subtract a y square, okay. So, if we do this, so here I have added, and since I have added, so I got I could use this thing, and then I have to subtract also, so minus a y square. Now, this part is f of y into e to the power of minus a y square, but however we have e to the power of minus epsilon by 2 y square and this term, okay, and we also had 1 plus mod y to the power 2n plus m. However, we know that since this is like inverted parabola, so this would as y increases, this would decrease fast, okay, and this would start dominating this, okay. So, this product of this polynomial term and this exponential decay term would be bounded, okay, between so it would be bounded between 0 and some finite number. So, that I can multiply that bounded that upper bound I can multiply with c and m to get a new coefficient d n m, okay. So, this modulus of these things is less than or equal to d n m into mod of f of y into e to the power minus a y square, okay. So, where d n m is independent of the choice of t x y, okay, such that t x is in b epsilon b beta t naught, okay. So, here what we have capital B we have used, okay. So, away from origin there, whatever t and x we choose from there, we would always independent of the whatever t x. So, this does not depend on t x, okay, because here the c and m etc. Does not depend on variables t x, correct. So, we would get d and m here. Now, there is a typo here. So, this is beta square. Okay. So, e to the power of beta square, correct, and other things are okay. 2 epsilon T1 square is fine. So, we consider this product C n m into e to the power of beta square divided by 2 epsilon T1 square into 1 plus mod y to the power 2 n plus m. Okay. So, what appears here, okay, into e to the power of minus epsilon square by 2 y square. I mean, this is actually basically saying that what is DNM. So, this is DNM. Okay. So, I mean, because this would be dominated by the decay of this. So, we can have this. Okay. So, now we know that this term, okay, mod of Fy, I mean this term, what is dn plus m, this thing, okay, since it is less than or equal to some constant times mod of Fy into e to the minus ay square, and since this is integrable, so I know that, okay, this part is dominated by one integrable function. Okay, this is dominated by integral function. So, we can use dominated convergence theorem for passing to any limits, etc. here in this case. Say, for example, if we want to take, say, sequence of x, okay, xn converges to x, etc. So, but that is dominated by this thing, okay, because here this would be a family of function of y, which is dominated by an L1 function, and that family would be, family parameter would be xn, okay, n. So, this whole family is dominated by this thing, because the right hand side does not depend on x, correct. Okay. So, it is dominated by one L1, yeah, it is not prime dash, it is L1 for uniformly in t and x. So, I just talked about x, but with t also you can do t1, t2, tn, a sequence which converges to t, and there also you are going to get this, you know. So, we can use that, therefore, dominant convergence theorem for appropriate choice of sequences to establish continuity of this map, that t comma x is going to f of y, I mean del n plus m del tn del xm ptxy dy. Okay. So, we can establish continuity of this map using the dominant convergence theorem. Okay. So, this is continuous, but where is it continuous? It is continuous for each and every choice of epsilon positive, beta positive, and t naught positive. So, whatever beta, epsilon, t naught we have initially, we have chosen those things just to get this, finite constant DNM, and for that we have obtained that, okay, this is continuous. But when you have obtained this continuity, then we got this property of this, this map. This map is continuous on this, ball B. I mean, this is also typo. I mean, this is B not greater, B epsilon comma beta comma t naught. Okay. So, this rectangle, and then it is true that this map is continuous on this rectangle no matter what is your parameter. So, parameter, then if you now decrease the parameter, all possible parameter, okay, epsilon, etc. So, you are going to get larger and larger, the rectangle, and if you now take t naught as close to as 0, okay, so you are going to cover the time t is equal to 0 part. If you take beta as large as possible, then you are going to cover the whole real line. And if you take epsilon also, as small as possible, so then T1, okay, is defined as 1 over a plus epsilon. So, as small as possible, then you are going to be as close as 1 over 2a, because this number is little less than 1 over 2a, correct. 1 over 2 times a plus epsilon is little less than, epsilon is positive, but if you take epsilon as small as possible, then the upper bound of the time limit would be as close as 1 over 2a. But of course, this time we cannot extend to infinity, I mean, it is not going to there, and we cannot assure also. So, what we have observed that b epsilon beta, this t naught, okay, is that rectangle, and if you take epsilon as close to as 0, then 1 over 2 plus epsilon would become 1 over 2a, 1 over 2a plus epsilon becomes 1 over 2a, and then union of these things is equal to 0. It is not sigma, this is 0 comma 1 over 2a, and here the strip for x, beta is as large as possible. So, union of all possible things would be just R, real line. Okay. So, what we have obtained is that this map is continuous on this 0 to 1 over 2a time interval and the whole space R. So, basically this function f of y, integration of f of y ptxy dy, okay, that thing without the derivative is the solution of the heat equation, correct, because that we have seen that, okay, this is the solution and the derivatives are like this, okay. I mean, here one can ask that, okay, where did I prove that, okay, the derivatives can go inside. Basically this is like, like induction kind of thing. So, you put n is equal to 0, m is equal to 0, then this is just this, okay, then also you get that this is continuous, okay, and then you put that n is equal to, say, it's like now instead of 0 you put 1. So, then you show that, okay, this is differentiable and the derivative. So, I mean this is differentiable, so the derivative is also continuous, you get, and then one after another you would proceed, okay. So, this proves that the solution of the heat equation is smooth, it is infinitely differentiable, okay. So, that is the end of the proof. Thank you.